Section 6.5, we're going to talk about exponential growth and decay. Exponential growth and decay occurs when we have a differential equation. Where the rate of change is proportional to the quantity. So an example of that would be an investment. Let's say we have an investment that earns 2.7% annually. And so this rate of change is proportional to the value of the investment. So we're going to write a differential equation that represents this situation. So we would have the change in the value over time is equal to 0.027 times the value. 2.7% of the value is how much the value is going to change. Now, we're going to solve that differential equation. When we solve that differential equation, one thing that I would encourage you to do when you solve a differential equation is leave a constant right where it is, if at all possible. And I think it's possible here. So we're going to bring the v over here, and we're going to have 1 over v, dv. And we're going to leave that 0.027 right over here. And we had multiplied each side by dt. So there's the separate phase. Now we need to integrate. So the antiderivative of our left side over here is going to be the natural log of the absolute value of the value, 0.027 times t. And then we have to have plus c. Since we aren't given an initial value, we're not going to be able to figure out what c is. But let's see now. We want to solve for v. We want to know the value of the investment in the future. And so I would think that I would change this from log form into exponential. And so the value would be equal to e to the 0.027 t plus c. Now that could be written as the value is equal to e to the 0.027 t times e to the c. That addition of the exponents means that it could be written as the same base with those two separate exponents. And that's pretty much where we could stop. I'm just going to take it one step further. I'm going to say that the value in the future, the value of this thing, e to the c, depending on what c is, this is going to be a constant for sure. I don't know what that constant is because I don't know what c is. But I'm definitely going to have a constant times this variable term, e to the 0.027 t. In order to figure out what c is, I'd have to know an initial condition, which I wasn't given in this problem. Now I'm just going to jump ahead a couple of slides. Because when we solve one of these situations where the rate is proportional to the quantity, whenever the rate is proportional to the quantity, the solution to the differential equation is going to look like this, where this base of f means the amount in the future. A sub 0 is usually the initial amount. Now, not always. The problem isn't always given to you. You're not always told what the value is at a time of 0. So what I'm going to call this is a previous amount. And certainly the amount at 0 is previous to any other amount. But again, we aren't always told the amount in the beginning. Now, K is the constant of proportionality. And normally we're going to have to solve and figure out what that value of K is. We're going to figure that out when we know some initial condition. And T, how much time has gone by? Okay, so this is the general formula that we're going to use to solve these exponential growth and decay. Those lend themselves very nicely because those are situations where the rate is proportional to the quantity. So let's back it up a slide now. Back up to here. And we've got a bacteria culture that starts, okay, we got an initial amount here, that's nice. 500 bacteria, grows at a rate proportional to its size, so that's good. That means we can use our formula right here. And after 3 hours, there are 8,000 bacteria. First of all, find an expression for the number of bacteria after T hours. Okay. Well, let's see now. Let's go back up here. We need a future amount, and the future amount would be considered this 8,000. And that's going to be equal to a previous amount. We'll call that 500. E to the K, now I don't know what K is, but I do know that this situation occurs, we have 8,000 at a time of 3. So I should be able to figure out what K is. First thing I would do is divide each side by 500, and then I grab my calculator and I figure that out, and I get 16. E to the K times 3. Now I could go from exponential form into log form, or other people look upon it as, let's take the natural log of both sides. And if I take the natural log of the left side, if I take the natural log of the right side, and so I've gone from exponential form to log form. And now to figure out what K is, and I'm not going to put this into my calculator. I'm just going to call this natural log of 16 divided by 3. It's a nice exact value for what K is. Yes, for what K is. Okay, so I need an expression for the number of bacteria. So the number of bacteria at any time is equal to the initial amount, or the previous amount, depending on what you did, e to the, and my value of K is the natural log of 16, divided by 3, times however much time has gone by. So that's really useful if I'm given a question that says, well, how many bacteria do you have after 4 hours? Well, I'm just going to take this 4, put it in there, grab my calculator, and figure out what that is. And if I figure that out correctly, you double check my work, but I think I'm going to get 20,000 159-ish. And since these are living things, I think running off with the nearest whole number is a good idea. So you double check my work. If you got to press pause, go ahead and do it. But make sure that we do indeed get this 20,000-ish answer. Now, when's the population going to reach 30,000? Oh, okay, interesting question. I get 30,000 as my future amount equals this previous amount, e to the natural log of 16 over 3. I don't know what t is. And I've got to solve for t. So if I want to get t all by itself, I think the first thing I'd probably do is divide by 500. If I divide both sides by 500, I really believe I'm going to get 60 over here equals e to the natural log of 16 divided by 3 times t. I think I'm going to go from exponential to log form by taking the natural log of both sides. And at this point, I think I'm going to multiply both sides by 3. And I think I'm going to divide by the natural log of 16. And if I do that and do that correctly, again, double check my work, I think I'm going to get a time of 4.430. Now you press pause and you figure that out and double check and make sure that I've come up with the correct value of t. Now, one other situation that you're going to run into in your homework, this lends itself really nicely to, is the concept of half-life, where rate of decay in terms of half-life, usually this is some type of a radioactive substance, and it loses half of its radioactivity, I believe, in a certain number of years. And this just keeps getting cut in half and cut in half and cut in half, which means it never loses it totally. So, half-life of radium-226, 1,590 years. Find the formula for the mass of a sample that remains after T years. Okay, so we've got this radium-226. And let's see, we've got 100 milligrams. Now that's the initial amount. So let's see, my future amount, one thing that I know is that after 1,590 years, my initial amount gets cut in half. So I got 50 compared to my initial value of 100. I don't know what K is, but I do know that the amount of time that it takes to go from 100 down to 50 is 1,590 years. Now I got to solve for K. So let's see, I'm going to divide by 100 and I'm going to get 0.5. I'm going to natural log both sides. And then to solve for k, which is generally my first job, I'm going to have the natural log of 0.5 divided by 1590. So my answer to part A is that the amount that I'm going to have at any time is equal to my initial amount, in this case it's 100, e to the natural log of 0.5 over 1590 times however much time goes by. Now, if you took your calculator and you found the natural log of 0.5 divided by 1590, you're going to find that that value of k is negative. When the value of k is negative, you've got a decay situation. The amount that you start with is going to get smaller and smaller and smaller. If the value of k is positive, you've got an exponential growth situation. The amount's going to get larger and larger and larger. Now for part B, and I'll do that in blue, find the mass after 1,000 years. Well, okay. The amount that we have after 1,000 years, 100 e to the natural 0.5 over 1590 times 1,000. Now, if I put that into my calculator, if I do that correctly, I believe I get something pretty darn close to 65 milligrams. And I know it gets cut in half in 1,590 years. So after only 1,000 years, it's not quite cut in half, and sure enough, it isn't. So I would think that answer makes some kind of sense. But again, double check my work, make sure I'm okay on that. Finally, when will the mass be reduced to 30? Well, okay, I'm going to do that in green. And my future amount is 30. My initial amount is 100. Now this is more than cut in half. I should get an answer bigger than 1,590. E to the natural log of 0.5 over 1,590 times t. And I didn't write it real well, but remember that this is an exponent on the e. I would divide by 1,000. Oh, sorry. Remember 1,000. That was 100. Sorry about that. When I divide by 100, I should get 0.3. E to the natural log of 0.5 over 1,590 times t. I would natural log both sides. Whoa, never. Natural log of 0.3. Natural log of 0.5 over 1,590 times t. And if I multiply both sides by 1,590, if I divide each side by natural log of 0.5, well, you see what you come up with. Again, I'm speculating it's going to be something greater than 1,590. And I'm getting something in the 2,761 year range, which to me makes sense. It is bigger than the 1,590. So that is how we are going to use exponential growth and decay. And you've got an assignment in Schoology. Go do it.